Okay, got it. Okay. So basically, what I'm trying to talk about tonight, it's a little bit about embeddings, similarity, and vector databases, and how all of them, all these building blocks, get together, and how useful they are with kind of like. I'm not gonna touch on how LLMs can use them, but and I'm just kind of more going more into the little building blocks and how they work. And I'm trying to keep it a little bit on the surface side, not too much detail, and in the presentation, and then in the code, I'm going to show some R&D code that I've done. I had an idea and just kind of developed it, and this is part of that. So let's start with the presentations. The embeddings, right? Uh, Anybody doesn't know what embeddings are? No. So I'm just kind of very quickly, they're just a list of numbers. So in here in the image, you see embedding and you see the list of numbers. Now, that's very useful for machine learning models and computers because they can really easily work with all those numbers. And they took off because the models that generate these embeddings are trained to extract more than just, let's say for a certain word, for a cat, they don't just extract the embeddings for the cat, for that specific word, but they try to build a context around it. And because of that context, now you can do different searches on it, and it's becoming very easy to find better solutions. Better search gets improved. Now you can do image search a lot easier. You can do kind of like audio files searching. Text especially, it's becoming quite a huge thing because for all the LLMs, they use these embeddings, and you're able to very easily just kind of figure it out. Like for the, Jeff, you were talking a little bit earlier about the chat part and to create like a longer term memory. Models have a short term memory. Depending on the model, I think right now the chat GPT it's at 8,000 tokens, and they have a GPT-4 model that they didn't release yet that's up to 32,000 tokens. And like you were saying, Philip, I think it was Falcon, the name of it. I remember reading about it, but I just didn't get a chance to try it. There was 100,000 embeddings, 100,000 tokens, which is quite huge. But for example, with a smaller model that doesn't have that much room, like GPT 3.5, I think it's like 3,000 or 4,000 tokens. So it's easier, especially if you have large chunks of text, it's easier to break it down, and using these similarity searches and the vector embeddings for the text, you're able to extract only the paragraphs, only the pieces of text that are very close to the question, and use those together with the question to provide a context to the model, and the model's accuracy is going to be a lot better. And that's used for like a chat history, where you can have a longer chat history and only certain parts that are pertinent to the actual current question are extracted. You can also do one kind of like development little project that I've done for a company that I work with was like a very fast search over a ton of PDFs and Word documents for due diligence. So they had a folder with 5-10 different documents, and they had a few questions that they really quickly wanted answered. So taking all that text, converting it to embeddings, and use that as a context with OpenAI, with ChatGPT, with OpenAI GPT-4, basically, not ChatGPT. They were able to get really quickly answers to their initial questions, and then somebody could go in and dig deeper. So they're extremely useful. And especially right now with this longer term memory, they're very, very useful for the current models. So like I said, they're just a simple list of numbers that are very useful for the way the models work and able to transfer the data. And the other big thing is 80% of the available data is unstructured. So social media posts, images, videos, audio, all of these can be converted in embeddings, and they can be, now you can do searches. GPT-4, they're calling it a model where you should be able to work with both images and text and other things. They still haven't released that multimodal part, but these embeddings right now, and especially with the model that's multimodal, it means that it would be able to search through both images and text and figure out what's most pertinent to what you need, which is another step forward. And like Cohere, their model for the embeddings, it's actually working, I think it was 32 languages. So that's quite amazing too, because you can do different searches in different languages, basically. So you have a text in French and you want to find all the information related to that text, but you want it in English. So you can actually get multiple language documents together into one single search. So all this stuff, it's kind of expanding nowadays. So to create them, you used different models, different neural networks that would do that. And basically, it's a very simple process where you have a piece of text, you feed it to a model, and the model will return this text embedding. Depending on the model, that embedding can have somewhere between 700 items in that list, up to a few thousands, depending on the model. Cohere for the text, I think it was about 700 to 800 length for the embedding, and OpenAI, it's like 1500. So especially if you're doing a lot of kind of text that the precision doesn't matter as much, you can go with a 700 model and save with a Cohere model and save on storage for these embeddings, because the most cost kind of prohibitive part of it is generating the original embeddings. Once you created the original embeddings and you upload them into a database, into a vector database, searches are very quick. You can just do an embeddings for your query and then really quickly do a search within the database and get the information from there. But that original embedding generation is the one that's a little bit more cost prohibitive in a way, and you want to do it once. So Cohere, again, just I think they dropped their prices by 1,000-fold. So that's quite a huge drop in price for their embeddings API versus the OpenAI. So that's a good thing to just try and work with. I haven't used them yet. I've been looking at their interface and all and the API, but I haven't used them yet. So anywho, if you guys have any questions, I forgot to mention this one in the beginning. If you guys have any questions, just interrupt. It's a lot. I would rather do that than have a ton of questions at the end. It's a lot better to keep it kind of like a discussion now. So, anybody have any questions until now?
Yeah, Anton, this is Raman. I got a couple of questions, bro. So,
yes.
First is when you're saying that you make a query to Cohere or OpenAI with a certain text. I presume that when you say text, you're talking about a token, or do you provide a sentence?
You provide the sentence. So, well, actually, I think no. You provide the sentence, and you are getting back the embedding. So I did the presentation from last month. I was showing exactly how you work with the OpenAI API, and that was one of them. So you just make a simple REST API call to their OpenAI endpoint, embeddings endpoint, and you pass a piece of text and you get back an embedding. That's
And okay, so I got that point. Now my question is, I mean, in the real world interpretation, I'm trying to interpret how this might be. So this embedding essentially represents all represents the meaning of the sentence.
yes.
In the sense that, you know, it may not be the exact words, but it means the same thing. So it could be different things, different words, different vocabulary, but it means the same thing, and they will do the search.
Yes.
Or maybe even in the context of like multiple languages, I might have asked something in English, it will translate into French, Spanish, and other languages, and you know the embedding will represent that. And so when the search happens, it will search for all these things instead of just strictly the text.
Right.
Is that a correct understanding?
Exactly. So that way, if you have like a keyword search, and if you don't find that specific keyword, your results are going to be pretty bad, right? If you have like a longer sentence, the chances of having that sentence repeating in your database are pretty slim. But once you extract the meaning and the kind of like the understanding of that, what that sentence is, it's a lot easier to find similar things within the database. So that's, they're calling it similarity search. So that also works with images the same way. So you're finding an image that basically the model is able to, let's say it's a cat on a green background and there is another yellow dog around, right? It will be able to figure it out that yes, there is a cat in this image, yes, there is a dog in this image, and there's also some sort of a green background. And based on that, starts looking at all the images in the database that have a cat and a dog, and then maybe a green background, or kind of like try to find all those. And the closer they are, so let's say it finds another one that has a cat and a dog and a green background, the similarity between those two images, between those two embeddings, it's going to be very close. So you will get a, we'll talk about that one in a little bit. So that way you will get the closest one. And then if there is only a cat and a dog, but not a green background, the number kind of like separates a little bit. It's not as close. And the same kind of like starts dropping down. So it's basically almost like sorting through the database based on this similarity, based on the embedding similarities. So that's kind of how it works.
Can you briefly talk to how OpenAI and Cohere created this? You know, I presume it's a AI model that sits behind this API.
Yes. Yeah. So they're using I think for the embeddings API, it's a little bit of an older model that's derived from, I believe it's derived from their GPT models, but it was specifically trained for embeddings. It was just fine-tuned to output these embeddings, right? So that's pretty much what you're doing. You're sending an API to them, they pass the data into the model, get the embeddings out, and then pass them back to you. So the models are just very, very large, kind of pre-trained and fine-tuned models for specific tasks.
And you were talking about, you know, number of data points that are returned.
Yes.
So this is essentially, you're talking about the size of the vectors, right?
Exactly.
Okay.
Yeah. So Cohere, it's about 700 something. OpenAI, it's 1500, and depending on the model, they can even return like a 1 and 0, just like yes or no. Depends on how it was trained, and depends on how it was just basically, yeah, trained to output what to output. So yeah, so there are different models, and each model will output whatever it was trained for and get an input from whatever it was trained with, right? So you have text embedding models that would generate vector embeddings, and then you have images, the image train models that are trained to get image and video and output embeddings, and the same thing for audio. For audio, one interesting thing is that they're using, I'm not sure if the latest models are still doing this, but they were converting the audio frequency to an image to actually do the embeddings off of that image. So it was a conversion that was happening, and basically that's kind of like what we're going to do in the sample as well. So I put some links here. I'm gonna put the presentation and the code up once, kind of like most likely tomorrow morning, and I'll put the links up in the meetup in the comments, so you guys can kind of take them and play with them and just kind of look at everything here. So that's basically how embeddings are generated. They're having pre-trained models that are kind of have inputs, specific inputs, and then output embeddings. Right. So
and then are there any standards for embeddings in terms of the dimensions or commonality across the different AI players?
not that I found. It's just it's pretty much every model. Every model, it's gonna kind of depending. In the end, I guess it's depending on what model do they use as a core, and if they change some of the stuff, some of these large LLMs, like for the Llama or other ones, I'm not entirely sure. I haven't played with the open source ones just because the results are not there yet. So I kind of stuck with the ones that kind of like, basically I stuck with GPT-4 just because of its performance. So I haven't tried others. And I've tried to look at them a little bit to see if they're up to par in results with GPT-4, but none of them were there yet. So that's why I haven't used them. But yes, pretty much every model has its own output, but all of them kind of tell you exactly what's the embedding, or what's the embedding size, and you will need that when you create the index for the vector database as well. So that's the thing that you need to know when you're using this.
So, and are all the numbers returned between 0 and 1 for every dimension?
Sorry?
Are all the numbers returned in that vector between 0 and 1?
Yes. Yes. Yeah.
So they're all normalized for every dimension.
Yes. Yes. So, right. So basically, yeah, I was just kind of like, that's an example that I put there, but you can see it in here. Well, actually, it's a minus. Sorry.
Oh, no, it's not.
Well, it's a minus.
Actually, yeah.
Yes. So it's still, I think it's between -1 and 1.
Okay, got it. That's right.
I don't know. Actually, that's a good question. I don't know. Somehow I didn't realize that these are negative numbers.
Wouldn't it depend upon what you're trying to encode?
Well, yes, they definitely would, and I have no idea what's happening behind the model and what makes it choose certain values. So basically, those are the ways that are being outputted for that embedding. And yeah, I don't know. I didn't actually, sincerely, I didn't even pay attention to the embeddings. All I've done was generating them and store them. And basically,
my understanding is with OpenAI, the way the transformer works is doesn't it? I think it takes the multiple dimensions, but it doesn't sit within like a unit hypersphere, and then there's some transform that then collapses it down to make to improve the what I want to say the compression of the data, to reduce the dimension.
Yes, yeah, they all of them do that. They all of them do that to a certain level. So yes,
So
yeah.
Anton, if you use Cohere, would you be able to apply that, I mean, use that embedding with any of the LLMs, or are they kind of like restricted now?
Well, you're not necessarily using the embeddings with the LLM. So the embeddings basically, you're using the embeddings just to do a search. You're
Okay, so
not.
are you limited on where you can search depending on which embedding you have chosen? In this case,
Yes. So if you start a project and you do embeddings for certain chunks of text and you start with OpenAI, you cannot switch to Cohere or the other way around unless you redo all the embeddings that you have stored. So they're just basically, each model has its own way of understanding that data and generating these embeddings. So the embeddings are unique per model. So once you make a choice of which model you're using, you'll kind of have to stay through it throughout the whole project. So unless you can add it as an extra layer in there and basically be able to switch between them. But you cannot say, hey, let's compare this embedding from Cohere with this one from OpenAI. They're different things. So that's what I was saying. So right now you generate all these embeddings and you end up with this huge list of embeddings. Next thing that you want to do, so like I was explaining in the beginning with the search, similarity search, you would need to find all the embeddings that are closer to that cat, right? So the cat and the dog and the green screen, you need to find all the ones that are closest. So there are a few methods to kind of like achieve that one. And these are the three main ones that are used: the Euclidean distance, the dot product similarity, and the cosine similarity. Math is not, you don't need to use the math or anything from this. I just kind of put it up here as kind of a reference. But what's happening, the vector databases, they've already built these ones in. And when you create the database and you create the index, you're telling it what type of similarity do you want to use. Do you want to use Euclidean, dot product, or cosine similarity? So there are a few differences between the three of them, basically. The Euclidean distance and the dot product similarity take in consideration both the magnitude of the vector and the direction. So they're better suited for stuff where you have like multiple units of one thing, where let's say you've sold this one item, but you've sold it 1,000 times, or you have a review for this one item that has, or you have this item that has a ton of reviews. And so when you're trying to kind of deal with that, it's in a way better to use Euclidean or dot product. Euclidean, it's not as much used with LLMs. It's or kind of like the vector databases. And from what I was reading, Pinecone uses cosine similarity and the dot product similarity mostly. So those are the two ones to choose. So the cosine similarity considers only the direction of the vector. So it doesn't care about the size. So semantic search, especially where it doesn't matter if you have one word or a paragraph of 150 words, right? They don't care about that one. They don't care about the size. They care about the meaning of that text. So that's why the cosine similarity is better for semantic search and document classification. So basically, most of the stuff that's kind of like it's going to be done, it's going to be done with cosine similarity for all the text stuff. And I haven't used either of the other ones in production or even played with them yet. So It's just the cosine similarity. It's very simple. It's very fast. And whenever you're generating the database, then they would create that indexing. So basically, now we're getting to kind of like the last building block, which is the vector database. So the vector database started in a way just from that index, and Facebook came up with this Faiss, which was just an index, in-memory index, which would allow you to keep all the vectors and run all the similarity searches in memory. But once you start, that works for a few documents or for a few hundred pages of text. But when you start getting kind of bigger project, a lot more data, images, kind of like video and other stuff, you will end up having problem with that. So that's why they kind of come up with a database, is that merges an old kind of like normal database that everybody's used with together with this index part, right? So they're just, the vector databases were specifically designed to be able to have that indexing, which would allow for very quick similarity searches between those vectors. So that's pretty much all they're doing. You're giving them a vector, and they're able to very quickly figure it out, which, so basically they create a cluster. The moment you input data into the database, the vector database, they automatically cluster it, and they automatically add that index in there. So now when you're coming with a new embedding, they're really quickly able to figure out, oh, this vector, let's say it's part of this dark blue here. And rather than going through the whole database, it's just going to search through that blue, and they have very optimized algorithms that would super quickly return the data. The example I'm using right now, just 6,000 images, and I just didn't get a chance to run it over. Originally, I had 2.6 million images running and uploaded to Pinecone, and it was returning the results within few seconds, 3-4 seconds tops. So it's very, very fast for the amount of data that you throw in. So yeah, so basically that's what they're doing. They're just, you push the embeddings into the database, they automatically index it, store the embeddings, and they also allow you to add metadata. So for example, for filtering purposes. And you'll see the example, I'm using the file name, and the file name has this big long thing description of what's happening within that file. But yeah, so they allow you to have metadata. So that helps you to kind of filter too. So it's another layer. And depending on the database, they do pre-filtering or post-filtering. Sometimes they figure it out that for some of them, it's a lot faster to do the filtering at the end rather than in the beginning. So it's just like, depending on the database, you can kind of read about what they're doing and how they're doing it. But basically, that's all there is. You take an embedding, it gets indexed and stored, and then you can query it and then just kind of post-process the data. It's a very, very simple thing. And popular that I found, Pinecone, Weaviate. Weaviate, it's another pretty big one, and it's gaining a lot of traction. The one that I like the most right now, it's ChromaDB, just because, are you guys familiar with SQLite? Just kind of like a very simple local storage that works kind of like pretty awesome for small project. That's how I kind of compare ChromaDB. It's a very simple, runs locally, doesn't need a lot of memory. It's just awesome from what I was reading. Then Melvos is another big open source one. Oh, so that's what I was saying. Pinecone, right now it's only hosted. You cannot run it locally. Weaviate, you can actually run it locally. They had a Docker file, and I think they were working into doing a hosting service for it. So Milvus, it's another open source one. I haven't used it. Redis, from what I learned, they just added the similarity search and the embeddings part to their databases. Novik is another big one. Quadrant, I haven't used either one of these. And then Faiss is that the Facebook one that's just the index and it's on memory. So those are kind of like the ones that I'm familiar with. So that's kind of it for the presentation. Do you guys have any questions on this?
Yeah, Anton, I got a question for you.
Yes.
I'm trying to imagine a use case and tell me if that makes sense.
Okay.
So let's say my organization has a ton of documents and
Okay.
I want to enable not keyword search, but more of a semantic search on it.
Yes.
So the process would be, would I, tokenize the entire database, create embeddings and store it in a vector database, and
Right.
then query the vector database via some kind of a protocol like SQL protocol, or maybe just programmatically query it and get the results. Is that kind of very high level make sense?
Yes. Yeah. Besides, I mean, each database has their own kind of like querying way. Most of these work with Python, so you'll see how the querying works. They have their own libraries that you can just kind of pip install, and you're able to use pip install Pinecone, pip install ChromaDB. It's very easy and straightforward to use them, and it's kind of like a pretty simple process of dealing with it. But yes, you would take the database, tokenize it, generate the embeddings, store those embeddings, and right now you can query that vector database and get similar. Well, actually, when you query it, you need to query it with an embedding. So every time you have kind of like a question or a piece of text that you want to query with, you have to generate the embedding, and then once you have the embedding, you can query it. You can query the database.
Got it. So if it's images, I can imagine each image is a token equivalent to a token, right? You get the embedding for that. But if it is documents, how would you chop it up?
So that's up to you. So usually you can use a tokenizer, and the tokenizer, you choose how many words do you want within each kind of like chunk that you're splitting. And also you can have some sort of an overlap between those. That's a whole other discussion, but yeah, you would break. So if you have a big Word document that has 50,000 words, you can break it down into chunks of 300 words and generate the embeddings for each and every one of those chunks. And then when you are doing the search, it would return those chunks, the 300 word chunks that are the closest to your question.
Okay. So, I mean, ideally you would say that you'll probably use a sentence each, right? Because just chunking it out arbitrarily by 300 words or something would not make sense. The logic will be
right.
a sentence each.
Yeah, well, I've seen examples of both, and they seem to be working. Oh. So it's quite interesting. I haven't really played much with it. The one that I've done, it just basically went to 300 words and that was it. And it worked good enough to just kind of give the person a list of, hey, this is your answer. And then here's a list of places where you can find in which documents and what page. Mm-hmm. So that kind of worked out. It was like a quick test, pretty much.
Hey,
So-
and then in your experience, how effective is it to do keyword search using the vector database compared to the traditional indexing on keywords?
I haven't tried that.
Hmm.
So that's something that, yeah, something that is basically the way this one was working was they would have a question that's a query to basically takes the query, the question, finds the embedding for it. Based on that embedding, it goes, looks to the text for the chunks that are similar, adds them to the context, and sends the context plus the query to OpenAI, to the GPT-4 API, and then it gets the answers back from there.
I see.
Yeah, and then in the meta, I had the document name and the page, so I can just kind of return that list of, hey, this is where those things are.
Got it. Another question is for the top three you mentioned, I think Pinecone is offered as a cloud-based service,
Yes.
while Weaviate and Chroma DB are like open source. You have to like run on your own compute instance, right?
Yes. Well, ChromaDB can run it on your machine. You don't need any Dockers. You don't need anything. It's almost like SQLite, where you just run it and it's fine. You don't have to do anything. Just pip install ChromaDB and then you can use it.
Mm-hmm.
So Weaviate, I think you needed to set up a Docker for it to have it run locally. And I know that they were looking at a cloud hosted version. I know that they were talking about it. I don't know if they launched it or not.
Got it.
Yeah.
Cool. Thanks.
Yeah. So, okay. So any more questions on this?
Yeah, quick one. When I noticed you write Faiss is index only. What do you mean by that? How does that compare to, say, ChromaDB, Weaviate, all the others?
Right. So remember how I was saying that ChromaDB or whatever, Pinecone, or all these other ones have two parts to it. They have a index part and then like a traditional database behind it that stores everything.
Uh-huh.
Faiss doesn't have that one, doesn't have that storage. It
Ah,
happens only, basically works on that list that you pass. You pass a list of embeddings and it works straight on it. And that's it.
I see. Got it. So it's all right.
So it's in memory only. The moment you stopped the program, it just erased everything.
It's almost like ChatGPT, where you have to pass it all the context in with if you're going to ask a question on it or something like that.
Right, right. No, I mean, the way I'm thinking of it even simpler than that. I'm thinking just like, you build a list in memory and you don't save it anywhere.
Mhm.
Next time you run the program, you have to go and just kind of like rebuild it.
Yeah.
So
Okay.
that's all. They're just kind of like, it's a collection of the tools that do all the similarities and everything based on a list of embeddings in memory. That's pretty
Okay.
much.
What do you typically use Faiss with? Like, I'm just, maybe this is a dumb question, but I'm just wondering, is it
I
like
haven't
normally
used it.
paired with something, or?
I haven't used it at all.
Oh, okay.
And that's why I was just kind of like, I was reading about all of these and just kind of trying to provide as much info as I could. I haven't used that. I was looking into trying something, but I haven't gotten to it the same way with ChromaDB. So, but yeah, it's just the only one that I have experience with is Pinecone. So, okay, well, let's try this one. It's a little bit, it looks a little bit cumbersome, and remember, this was R&D code that I just kind of copy pasted and kind of made it work. So the whole idea was I wanted to test the hypothesis where some time ago, like I was saying in the beginning, I worked with Jay at a hedge fund, at a crypto hedge fund, And one of the things that we were looking at a few years back was converting the trade data into a graph and running machine learning algorithms on it to try to make predictions, or finding some sort of a pattern repetition or some other stuff. So I'm like, hey, what if I take this historical crypto data, open, high, low, close, volume, and trades, right, or HLCV data, and generate this kind of like little chunks. So what I'm doing here, if you look here at the steps and the duration. Now, okay, let me start from the beginning. So I have the data, and I'm going to use the data that I'm using is every 60 minutes. So every hour, I have a row of data, right? So I want to create this every 10 hours. I take a list of 60 rows, right? Originally, it was supposed to be done on a minute, where I would take every 10 minutes, I would take a list of 1 hour of data. But that was 2-point-something million rows, and it would have taken me forever to run it today. So I just kind of chose the hourly data because it ran a lot faster. So what I'm doing, I'm just creating these lists, right? Every 10 hours, I'm taking the last 60 hours. And with those, I am just generating this kind of like, well, basically what I'm going to end up doing, I'm going to end up creating graphs for each and every one of those. So if you see here, that's pretty much what I've done, where I'm just creating a plot with all those for each and every one of those images. So here, if I'm going to images, you can see this is one of them, right? So I've represented the data, I've put some moving averages behind it, and at the bottom I have the volume. And these are, you actually see it, how it kind of flows as a series, right? So, because every one of them, it's kind of like 10 minutes apart, and it takes the last 60 hours. So that's what I'm generating. So I end up with a list of, I think it was 6,134 images. And for these ones, so one of the biggest thing, I had to use multiprocessing to run all these, otherwise it would have taken forever. And for each and every one of these images, I will generate embeddings, right? So I'm generating, for now, I'm still prepping it up. I'm still prepping up my data frame, where I just create this large kind of like file name that would be what I'm going to use for meta. And then once I have all those, I'm going to use image2vec, which runs on top of PyTorch. And for each and every one of those images, I'm going to end up generating a vector. So basically, this is my model, image2vec, and it's going to run on the GPU. Then that's the file that it needs to deal with, convert it to RGB, and it's passing it to the image2vec. And this vec, it's going to be the embedding back. It's very simple, very straightforward, nothing fancy. And then in order to be able to do this, I'm going to, again, run multiprocessing. So what I'm doing here, I'm splitting it in 300 chunks, that whole data frame. So each chunk is going to have whatever, 6,134 divided by 300. So 60 something, I believe it was. No, I don't know how many. But depending on those, I'm going to end up with a set of chunks, which are data frame chunks. And right now, I'm just bringing them back together and create my data frame again, right? So, and well, actually, I have 12,000 rows. And See, here are the embeddings. And basically, we can look at this one. Okay. No? Oh, embedding. Okay. Live coding. Don't do it. So this is one embedding, right? So this is one embedding generated from image to vec module. And if we look at this, this one has 512 elements in that vector. So the length is 512. So like I said, pretty much every model is going to generate its own set of embeddings. So, and now the Pinecone implementation, it's just basically I'm reading this data frame. I had the code split into multiple things. So rereading that one, and then I'm converting it. I think I had an issue where the vector was not a list, so I'm just converting it to it was a NumPy array, and I've converted it to a list, and then just basically creating the meta with the file name, right? So right now you're gonna see that I have the file name in there for it. And again, I split this one in 100 pieces so I can run multi-process it, and then I can just run this and send it in. Let me see, where was my interface? Oh God, Pinecone, there it is. So this is the Pinecone, and you can see that it just kind of just created this graphs in this name, and it has the 12,000. I doubled it up, so that's the problem. I ran it twice, and I doubled up the vectors, which is kind of like a bad thing, but it's gonna take too long to rerun. So, but yeah, so basically here, to just create this, you'll have to init the Pinecone object, pass the API key, and the environment. The environment, it's a very kind of like a tricky one. It took me a little while to figure out where it was in the beginning, but that's part of their, now they changed the name to environment, so it makes a lot more sense. Before it was, I don't remember what it was called, but I remember.
1, 2, 3.
Sorry?
Oh, sorry, my bad. It's supposed to be muted.
That's fine. So, so yeah, this that's the environment. It's important, and then you just basically pass the index name when you generate it. Dimensions, like remember how I was saying that you need to know how the size of your vectors. So this is 512, and it's part of the initialization. And they have a pod type. They had, I forgot right now what the differences were, but depending on, they had, I think they had a P1, P2, and P3, where P1, it was the lowest and the slowest, while P3 was the most available and fastest. So just like for test, I didn't need that. And by the way, Pinecone allows you to have, I think it's one index that you can get for free for your account. After that, you have to pay for. So it's, you can test and play with it. So basically, well, actually, this should have deleted the index. I'm not sure why I doubled it up. Maybe I ran stuff out of order here. And then this is the creation of the index, and you get the indexes back. And once it's done, usually this operation takes like 30 seconds to a minute. Takes a little while for it to actually create the index and set everything up. And then this is one another kind of like thing that they were asking for. Before you querying it, you must connect it, and you would kind of connect it that way. And then right now, for each and every one of those data frames, I am pushing them to the database with just this index.observe. And there were 100 of them, and this one I think it took somewhere in the 30 seconds range. So this was not async, but I'm assuming you can actually make this one be async, but I don't really see the need for it, especially that you're doing this as a one-time only usually, and then you update. When you add more data, you can just add to it. So you don't have to do it all the time. And then once you run through it, it gives you, I mean, this describing the stats, gives you the information about it. You can actually see it here in the UI as well. And then for the query, it's a very simple thing where you just kind of query what's the vector that you query with. This is your embedding. How many do you want back? So if you want to include the values where the actual embeddings back, I didn't want for this. I just care about the metadata, and that's it. Just kind of like the sorted on the metadata. And because the metadata is the file name. So with that one, I can actually look at my images. So here, if I gonna do it a little smaller, this is the original one. And then kind of like this is the closest to it. So if you see, it's, well, actually, no, sorry, this is my query, and this is the same thing because it always returns your 1.0 similarity. So it returns, if it's in the database, because, sorry, I queried it with one vector that was already in the database. So I queried it with the first vector in the database, right? So that's why I'm getting this one back. And then from here on, these are kind of like the similar one. And you see they're pretty close to one another. They're using the same sloping. A lot of the data, it's very similar. And then this is kind of the same. Well, actually, this is the same image. Not entirely sure why I got that one in there. And then this is another different one. So let me see. Maybe I need to rerun this. You know, this is the same.
Well, it's because you ran it twice. You entered it in twice, right? So each one's
yes,
gonna
that's true. That's true. Thanks, Jay. Right. So yeah, and you can see it here. So yeah, so basically this is it. It's very kind of straightforward. It's nothing fancy about using it and implementing it. It's just the overall logic of how to use it. That's the one that's a little bit more complex. But to actually implement the code, it's very straightforward. Their documentation is very, very well put together. And they also have a ton of examples on how to use it with kind of different use cases. So it's very, I really like what they've done, the Pinecone guys. So, any questions?
Anton, a quick question.
Yes.
So you converted the data into image, and then use the image to pull embeddings.
Yes.
Could you not have used the data itself as if they are tokens to create an embedding?
Well, the data itself would have been a series of open, high, low, close data together with all the moving averages and volumes and all that stuff. So you could use them if you have a model that's trained and fine-tuned on this type of data, right? So I was trying to take advantage of models that are already existing, and they're doing the clustering and they're doing all this similarity on what's it called, on images. So basically it was just like a trick. I was trying to convert this data into a graph. That was the simplest way for me to use a pre-existing model with this different type of data.
Okay, so essentially you are working back from where you could get the best similarity comparisons.
Yes.
And
To a
okay,
certain point, yes.
I can relate to that, yes.
Yeah. So yeah, that was the whole idea, and this was a big thing a few years back where the models that were dealing with computer vision, they were the best ones out there, the best performing out there. This was before LLMs took off. So you had all that, the VGG and all these other kind of like CNNs that were doing really amazing job on computer vision. And a lot of people back then, they were like, oh, if we can take the images and can train your own models and do all these things. So for me, it was like, hey, there are already models out there that do this. So let's just kind of piggyback on that and see how it works and if it works.